Hello and welcome to another Stat 253 video. This video introduces decision trees, specifically regression trees, which will nearly bring us to the end of regression methods for this class. Decision trees are a non-parametric method, sometimes referred to as a rules-based method. Decision trees are really just a complicated list of if-else rules that bin observations together. Observations in the same bin, which are also called nodes or leaves, have the same predicted value. In the regression trees we will discuss, the predicted value will be the average of the response variable for that node. One of my favorite aspects of this modeling method is the ease with which you can explain it to other people, including people with very little statistical training. This is largely due to being able to display the results in a nice graphic. Let's take a look at the simple regression tree we have here. This is using the MPG data we have seen before. In the top node, we see some details about the entire training data set. The 100% means that 100% of the data is contained in that node. The average MPG for the entire training dataset is 23 miles per gallon, as indicated by the 23. Beneath the box, we see the first split. Displacement is greater than or equal to 2.6. Observations that have a displacement greater than 2.6 follow the yes branch to the left in this diagram. Those that don't follow the no branch to the right. Focusing on the yes branch, we see that 55% of the data end up in that node, and the average miles per gallon is 20 miles per gallon. This node is then further split on displacement being greater than 3.9. If it is, the observation falls into the node on the left, where 22% of the data reside, and the average MPG is 17. Observations with displacement less than 3.9, but still greater than 2.6 from the initial split, fall into the second node, where 33% of the data reside, and the average MPG is 21. The tree continues splitting until some stopping criteria is satisfied. To use a regression tree for prediction, a new observation would follow the path until reaching a terminal node, which is a node that has no branches coming out of it. That node's average response would be its predicted value. So, for example, a car with a displacement less than 1.9 would follow the path indicated in red and would have a predicted MPG of 32. I'm sure by now you are wondering how we decide to make the best splits in the tree. We have two goals. 1, make the observations within each node as similar as possible, and 2, make the nodes different from one another. We will do this by finding the split that minimizes the sum of the squared residuals, shown in the bottom equation on the left. Relating our example to this equation, let's look at the first split. Here, x sub j is displacement. S equals 2.6. R sub 2 is the node with the observations with displacement greater than or equal to 2.6, and R1 is the other node. The SSE can be computed by subtracting the average MPG for the observations in R2, 20 miles per gallon, from each observation in R2, squaring that quantity and summing over all the observations. Do the same for R1, where the average MPG is 27 miles per gallon, and add them both up. Any other split with any other variable would have led to a larger SSE. This splitting process would keep going until a reasonable stopping criteria is reached. Speaking of stopping criteria, how do we decide to stop? First, why would we want to stop? Like the tree we see here, if we don't stop, we will end up with nodes with very few data points in them. What do you think would happen if we tried to apply this to a new data set? Yes, that's right. It could perform poorly on the new data because we might have overfit the model to the training data. There are many methods to decide when to stop. We will use a parameter generically called CP, which stands for complexity parameter. In regression trees, the overall R² must increase by at least CP at each split. If it does not increase by at least that much, it will not create the split. We can test different values of CP in our usual way using cross-validation. So in this method, CP is our tuning parameter. In R, we will use the standard train function from the caret package to fit the model. We specify a decision tree by using method equals rPart. The plot illustrates the tree constructed using the CP parameter with the smallest cross-validated RMSE. The table shows the various RMSEs for different values of CP. Although regression trees may seem simple, they are a key building block in more advanced machine learning methods like bagging and random forests. We will discuss both of those next week. That concludes our video for today.